In this video, we generalize our calculation of derivatives to work for any arbitrary value of x. And this means we're actually looking at the derivative as a function of x, and we're going to call that f prime of x. So we're going to get comfortable with calculating these things, but because the derivative is a function of x, we can also plot its graph and then explore the relationship between the graph of a function and the graph of its derivative. So to start things out here, this is just a quick reminder of what we were doing with derivatives in the previous video. So what we did was learn to compute the derivative, in other words, the slope of a tangent line at a specific value of x that we called a. Now there were two different ways to write this, but either way you write it, the limit is expressing the same exact geometric idea. We take the slope of a secant line between a, f of a, and a nearby point, and then we shrink the interval width to 0 in our limit and obtain the slope of the tangent line, and that's the derivative at a. So in our first notation, we called the right end of this interval x, and we computed the slope of the secant line, taking a rise there of f of x minus f of a and a run of x minus a. And then we shrank the interval by taking the limit as x goes to a. In our second notation, we called the interval width h. And this means the right end of our interval was a plus h. And we computed the slope of the secant line, taking the rise of f of a plus h minus f of a over the run, which was h. And in this notation, we shrink our interval width to 0 by simply letting h go to 0. Now the generalization we want to make is that we want to write down a formula for derivatives that's valid at any arbitrary point x, and we're going to call that f prime of x. So basically, we simply want to replace a with x. But notice that our first formula has a problem here. We already used x as the variable right end of the interval in our limit. So this is why all the calculus books normally use the second formulation here. And so we can simply replace the a with an x in that formulation of the derivative, and it doesn't cause any problems for us. So there it is, a formula for the derivative of a function at any value x. And of course, the geometric idea is the same old thing, but this time we're going to use an x for the fixed point on our interval. We use an x plus h for the variable point on our interval. We compute the slope of a secant line by taking the rise over the run between those 2 points, and then we take the limit as h goes to 0, and we arrive at the slope of the tangent line at x. So here's a quick example. And in this example, we're given a function f of x equals 1/4 x squared, and we're asked to compute f prime of x and then use our result to find f prime of -2, f prime of 0, and f prime of +2. So we just start things out with our new definition of f prime of x for any point x. So there it is. The limit as h goes to 0 of f of x plus h minus f of x divided by h. Now all we have to do is evaluate our function at these two values of x plus h and x. And when I sub in x plus h for x in the formula for f of x, I end up with 1/4 x plus h quantity squared. Then I subtract from that f of x, which is 1/4 x squared, and we're still dividing by h. Now remember, these limits by design are always going to give you the indeterminate form 0 over 0. In other words, if I just replaced h with 0, that numerator would be 0 and the denominator is 0. So we always find ourselves having to go through some kind of algebra trick to get around that indeterminate form. And the basic strategy for this one, well, I'm going to start by factoring a 1/4 out in front, but then the basic strategy is to expand that squared binomial and then combine like terms, clean things up as much as you can, and hope that an h cancels out. So when I square x plus h, that means x plus h multiplied by x plus h, and that generates a cross term. You can't just square the first and second terms. So I end up with an x squared plus 2xh plus h squared, and then in my second term I just have a minus x squared. Remember, I factored out the 1/4. And we still have an h in the denominator. And I see something good happening already. My x squareds are going to cancel out, and this means both terms in the numerator have a factor of h in them, which means I can cancel my h. So I'm going to go ahead and factor out one of those h's just to really highlight the cancellation here. And I end up with h times the quantity 2x plus h in the numerator, and then there's just an h in the denominator. Now I can cancel one of those. And I end up with 1/4 times the limit as h goes to 0 of 2x plus h. And at this point, direct substitution of h equals 0 doesn't cause a problem anymore. So I can just go ahead and do that. In other words, my h is just gone, and I end up with 1/4 of 2x, which then simplifies to 1/2 x. So there's a formula in general for f prime of x at any value of x. F prime of x is equal to 1/2 x. And now we can get into our follow-up questions. We were asked to find f prime of -2. So all we have to do is replace x with -2. That gives us -2/2, which is -1. So apparently the slope of the tangent line to our original curve at x equals -2 is a slope of -1. Next, we can look at f prime of 0 and replacing x with 0 in the formula for f prime of x. That just gives us 0. So apparently we have a horizontal tangent line at x equals 0. Finally, we get f prime of +2, and this gives us 2/2 or +1. So the tangent line on our original function has a slope of +1 at x equals 2. So notice how cool this is to have a general formula for f prime of x. We can just plug in any x value we want, and we immediately find the slope of f of x at that point. So now that we have this general formula for the derivative at any value of x, we realize that the derivative is itself a function. In other words, you plug in x values and y values pop out, but now the output values are actually the value of the slope of the original function f of x. So in our example, the original function was f of x equals 1/4 x squared, and the derivative was f prime of x equals 1/2 x. And we can visualize both of these functions in a graph to verify their slope relationship. So we have the graphs of both of these functions, and now we can check our 3 specific values from the example. So first we look at x equals -2. And so I've plotted the tangent line on the original function f of x at the location of x equals -2. And I can see the slope of this thing just by counting squares here. Every time I go down one, I go to the right one. So the slope of this thing is -1. Now if we look at the graph of f prime of x, I see the correct value there. I'm at x equals -2, and then the vertical value on this graph is -1. So the y value on the graph of f prime tells me the slope on the graph of f. We continue with x equals 0, and there's our horizontal tangent line again, in other words, a line with a slope of 0. And I see the correct point in the graph of f prime of x, so the y value there is 0. Again, that y value of 0 corresponds to a slope of 0 on the graph of our original function f of x. Finally, we look at x equals +2. And I can count squares again to see the slope of the tangent line here. Every time I go to the right one, I go up one. So this tangent line has a slope of +1. And again, that corresponds to the y value on the graph of f prime of x. It has a y value of +1, corresponding to that slope of 1 for the tangent line on the original graph of the function. Okay, so the relationship is making sense here with the few points that we tried, but it's instructive to look at this as an animation that covers every value of x in the graph. So we can see as we cover all the x values from left to right, the vertical value of f prime of x, in other words, the output value, is always the same number as the slope of the tangent line on f of x. So here's one more example exploring this relationship between f and f prime. This time we're given the graph of f and we're asked to sketch the graph of f prime. And it's really useful in a problem like this to look for the zeros of f prime. Those occur when the slope of the tangent line to f of x is 0, and those are pretty easy to spot. So we see 2 locations where we have a slope of 0 on our tangent line. In other words, a horizontal tangent line on f of x. And so those 2 x values correspond to zeros of f prime. So the derivative is equal to 0 at those same x values where the slope of the tangent line is 0. Now, once you have those zeros, you have to do a little bit more slope reasoning on the original graph of f of x in order to finish your sketch. So I'm going to look in the leftmost region here and ask myself what the slope of f of x is doing. As I go from left to right in this region, I always have a positive slope on my tangent line, but that positive slope is getting smaller and it eventually hits 0 at this special value of x. So what I need in my graph of f prime is a function that is positive but getting smaller. So it's a decreasing positive function here. And we continue this reasoning in between the 2 zeros. In this region, the slope of the tangent line is always negative. And somewhere around here, somewhere around x equals -1/2, I reach a maximum negative slope. In other words, it's the steepest descent at that point. And that means on the graph of f prime, I'm going to reach my largest negative number on that graph somewhere around x equals negative 1/2. We then continue by thinking about the rightmost region on this graph, and that's where the slope of the tangent line becomes positive again. But initially, that's a small positive slope when I'm coming out of that minimum of the function, and then it gets steeper and steeper. So f prime is going to become positive again to the right of this point, and then it grows larger and larger as we continue to move to the right. So that's enough reasoning to make a decent sketch, but let's illustrate with a final animation. So we're running through x values from left to right, and we can see our tangent line on the graph of f of x, and each value of f prime of x is equal to the slope of that tangent line. So we're pretty much getting what we expected here. F prime is positive and decreasing to the left of the first point, reaches a maximum negative value between the 2 points, and that's happening somewhere around x equals negative 1/2, and finally it becomes positive again and increasing to the right of our second point. If you enjoyed this video or at least found it useful, check out another one by clicking one of the links on the left, or click the Zach's Lab logo on the right to explore dozens of physics and math playlists. As always, you can leave your questions, comments, and requests in the comments section below, and I'll get back to you within 24 hours. Thanks for watching Zach's Lab, and best of luck on your math and physics journey.